from MIT, then please.
Good afternoon. I take it people can hear me okay? That's good. I'd like to start by thanking Jean-Paul Lamont for a chance to come participate in this workshop. I'm quite nervous because I'm not going to do anywhere near the complicated mathematics that you saw this morning, so we'll see how this goes. But I've been working in the area of movement control for quite some time, and I keep coming back to the same problem that keeps showing up, and that's what I call the paradox of human dexterity. Now, you may or may not know it, but humans have extremely slow muscles. Muscle bandwidth is about 2-3 hertz, certainly less than 10 hertz. Compare that with electromagnetic bandwidth and electrohydraulic bandwidth of 100 hertz to a kilohertz. You can get up to a kilohertz and beyond with electrohydraulics. Compare that with, say, feedback loop delays in mechatronics, milliseconds long. Transcortical, 100 milliseconds or greater. And now you compare the behavior you get with robots with humans. So we have slower hardware, slower neurons. Arguably, we have slower brains. Yet we vastly outperform the best state-of-the-art robot. I mean, I don't think anybody would object to or argue with that fact, right? So how do we do it? I mean, what's possible? And if you think this is the real question is, remember that these delays imply predictive control of some sort based on internal models. Well, the question is, what kind of internal model? This is a young man. This is Adam Weinrich. You'll find him all over the place on the YouTube, which is where I stole these videos. He's an expert with the bullwhip, and he's able to hit a playing card and knock an egg into a cup, or hit the top off of the cap off of a bottle of water. My point here is that if you look at this, the complexity of his model of the bullwhip is just astonishing. It's even more impressive if you look at, I forget the name of this. This is one of the Olympic competitors from, Dagmar help me out, I forget which one. And look at what she's doing with that ribbon, and look at the complexity of the control. Now, imagine let's put engineer hats on now for a minute and say, okay, I'm going to come up with a model of either the bullwhip or the ribbon. So I'm going to have to come up with a continuum model. I'm going to have to deal with interaction with a compressible gas, which is air. The compression of the gas is important because the bullwhip makes a crack. I'm going to have to do, if I was to do an engineering style model, it's going to be a continuum model involving fluid structure interaction. I don't think I could even find a modern day supercomputer that can compute that in real time. Right? That's a hard problem. And yet here we have two humans who are able to not only manage it, but they can do spectacular things with it. So what's the trick? I mean, how are they, or we in general, doing it? So let me go down one. So one of the questions that has interested me for quite a long time is, so what is the form of internal models? I mean, I firmly believe we have to have them because we can do predictive control. If you don't believe that, then think of how one of the popular sports in the United States is basketball. And you have these guys who are very good at standing a long way away from a little tiny hoop and throwing a spheroidal object from here into that with very high reliability. And once you let go of the ball, it's all over, right? So that had to have been done as predictive control. And the delays in the nervous system imply that even normal movements are predictive control is a big part of them. But the question then is, okay, so what's the form of that control, and what's the underlying geometry? The reason I bring up geometry is because all of the mechanical physics that we heard about this morning assumes that you have a Riemannian geometry underlying it. And my question then is, well, fine, but is that necessarily what's underlying human motor control? So with colleagues quite some years ago, we addressed this question by studying haptic illusions, and we basically tested, could we find evidence whether the underlying geometry in human behavior was Riemannian or not? Haptic, so haptic is, I'll try and explain a bit. I'm looking at the interaction of motor and sensory. So when I want to feel something and determine, for example, its shape, that's called haptic exploration. So I can think of tactile defining as identifying contact or looking at forces. But when I combine that with motion, I can derive shape. So that's generally the interpretation of the word haptic. Don't know if that answers you. Let me continue and maybe it'll become clear. So if you ask subjects to feel objects, it's been known for some time that they misjudge the lengths when they feel objects. And in particular, if you ask, the radial lines are judged to be longer than tangential lines. So if I give you a square object to feel, then you will misperceive that object as not being square. The reason this is important is because the illusions may tell you something about the structure. They may tell you something about the postulated internal model about how it's organized. And the specific question we asked was, is haptic perceptual distortion geometrically consistent? And I have to explain what I mean by that. So here's what I mean by consistent Riemannian geometry. So Riemannian geometry allows distortion, so lengths don't have to be the same in all directions, but it does require consistency. So if I was to ask you to feel a rectangular object, and you decided that this length was the same as that length, then to be consistent with Riemannian geometry, if I asked you to judge this angle and that angle, you'd have to also judge those to be equal. So equality of lengths implies equality of angles and vice versa, right? So this is fundamental to Riemannian geometry, and if I'm misstating this, I'm sure Daniel will be able to correct me on this. But basically, consistency requires judgment of angle and judgment of length to be predictable one from the other. So here's what we did. We used a planar robotic device, and we used it to simulate rectangular holes. These are virtual holes, not real holes. Asked subjects to just feel around the hole and tell us which side was longer. Did that with a forced choice paradigm, so they had to tell us a yes or no in one direction. Then we gave them a whole range of rectangles, from skinny rectangles to squares to long rectangles. Did that with the rectangles oriented this way relative to midline and oriented at 45 degrees. That gives you sufficient information from which you can deduce the metric underlying their perception, and you can express their metric, at least locally, by an ellipse. And the ellipse, you can think of it as a subjective circle. So if this is the ellipse that we got from our measurements, that's what the subject thought of as a circle. Is that clear? Okay. So what we found was, this is with 8 subjects, that the subjective circles, they were very consistent across subjects. They were distorted, not a whole lot, but enough to make a difference. The subjective circle was an ellipse with eccentricity 1.3 and angle 17 degrees. You know, not terribly distorted, but not circular. So the key thing here is that we do have a perceptual distortion. It's highly consistent across subjects. Then we did a separate experiment where we took advantage of the fact that with a robot you can do things that you can't do with real objects. And we asked subjects to feel simulated triangular holes. So the hole was triangular, but it was a sort of a magic object in the sense that you could feel this angle, you could feel that angle, but you could never get at that right angle corner, because whenever you were on this edge, that edge went on indefinitely. If you were on that edge went on indefinitely. And the reason we did that was to make sure that our subjects couldn't kind of cheat by measuring length and deducing angle. So we wanted them to actually sense the angles. So this is the important thing here. The right angle corner was inaccessible. Then we did the same thing as before. We gave them a series of these right triangles ranging from obtuse this way to acute that way, and did the same thing at 45 degrees. That gives us also enough information to identify a metric. And the key point was that we could identify a metric, but 2 things happened. One is that the variability across subjects went up substantially. And secondly, the average subjective circle, it was again elliptical, but it was at a very different angle. And in fact, I can go into the statistics if you want. I have that in later slides if you need it. But what we found was that with a very high statistical significance, the judgment of length and the judgment of angle were not consistent with the Riemannian geometry. So I think this is kind of an important point. So what we have is, okay, so I think it's fair to say that Riemannian geometry is the foundation of all mechanical physics. It's certainly at the basis of Hamiltonian mechanics, Lagrangian mechanics, but at least for haptic perception, that is, this feel and judge shapes, the brain's model is not Riemannian. And that's kind of a shock, right? Because if you have all these ideas of internal models based on back computation through computed torque models and so on, well, yeah, but we don't have the basic geometric foundation for that. Yet humans do quite well at managing dynamic objects. So what's the trick? Well, one of the alternatives that my colleague Dagmar Stern and I have been working on for some time is the notion of seeing if there's a kind of a workaround provided by intrinsic dynamic behavior that would emerge from, for example, neural networks. So the basic story is, look, at a minimum we have long communication delays in the neural system. Neurons communicate at about 100 meters a second, ballpark, that's fast. And that means that in a certain sense, my brain is teleoperating my body, right? My brain is about 1/10 of a second behind in listening to the sensors and about 1/10 of a second behind in talking to the actuators. Rough numbers. So if I have those long communication delays, that really impairs my ability to do reactive feedback type control. I mean, we do use feedback, but if you want to get highly dynamic behavior, you can't count on it. So instead, these primitive dynamic behaviors may provide a workaround. And by primitive dynamic behaviors, I mean things which are attractors of a nonlinear system. One could be a point attractor. Professor Friston talked about point attractors this morning. You could have limit cycles, they would give you rhythmic oscillation. But there's a much larger set of possible attractors, and one of which is impedance, which I'll talk about later. It's my favorite topic to talk about for the last several decades, and it allows you to control interactive behavior. So the question is, so how would these primitives help? I mean, would this be a solution to the problem? So the idea here is that if I evoke these dynamic primitives, they may require minimal central control. So I could sort of fire them, and I'm not going to forget them, but I'm going to only intervene with the periphery once in a while. I may monitor continuously, but I'm not going to keep sending down commands. And so that means that the brain, which is not very fast, doesn't have to continuously intervene with the periphery. And that, yet I could achieve high performance if each of the primitives is itself a highly dynamic behavior. So I get this low-level behavior that's dynamic and fluid, and I only talk to it once in a while. And that may be consistent with one of the easy observations you can make, and that is if you try to imagine you develop a skill and then you try to explain to somebody what you're actually doing, if you think about coordination, you usually impair coordination. It's very difficult to actually think about things while you do them. At least I find it that way. And maybe what's going on there is if I keep thinking about it, I keep interrupting the process that's ongoing. I'm speculating here, but this is the idea that the dynamic primitives give you dynamic behavior, and the central controller can act sort of like a supervisor. It doesn't have to be continuously involved. Any biological evidence for this? I'm going to go over this fairly quickly, but part of what got me interested in this was work that I had been doing related to neurorehabilitation and developing technologies to help people recover after neurological injury. We used robots that can safely interact with humans to provide physical and occupational therapy to patients as they recovered after a stroke. Long story there, I won't go into it. But the key thing is that the robot then interacting with the human provides a measurement platform, so we can measure the earliest movements made by stroke patients as they start to recover after a stroke. And the very surprising thing that we found was what you're seeing here. This is data taken from a lady who was this is 6 weeks after her stroke. Up to 5 weeks she had no movement, but we're still able to provide therapy with the robot, and now she begins to recover. As part of our robotic therapy, we also include evaluations where we ask the patients to do simple movements like, say, draw a circle. This is this lady's circle at 6 weeks post-stroke. And this is, you're looking here at a plan view of the path of her hand, and here this is the speed along the path. The speed profile is a function of time. And what you can see is this is not a very circular circle, but this is actually good news. This is movement. Previously, she was not generating movement. But you see how it's sort of broken up? There's kind of like corners in the path. And those correspond to, here we have a speed profile where you have a peak and a little valley and a big peak and then a little valley. And then you actually get a complete stop at this point. Another peak and peak and peak. So the movement is quite fragmented and broken up. We continue the therapy. This is the same lady at 11 weeks post-stroke. And now what you begin to see is that there is some recovery taking place. This is her circle, and it's not yet perfectly circular, but it's a whole lot smoother and circular looking than it was at 6 weeks. And the speed profile, it's not, again, perfectly smooth, but notice that the dips don't go all the way down to zero. She's not actually stopping. So what you're seeing is that there's clear evidence that the earliest movements are fragmented in some way. We took a look at that kind of behavior, and we measured from the earliest movements, the earliest simple reaching movements made by 20 patients. One of those patients never recovered, so they go out of the data set. We found the peaks in speed profile, extracted that from the data, fit a beta function to it, and what you find is that the shape of this speed profile is highly stereotyped. Shape parameters are within 10% for all subjects. So this is a highly stereotyped chunk of movement that we're seeing in 19 stroke patients with vastly different lesions. So this is something kind of fundamental that we're seeing here. And it turns out that it gives you a good way to track the process of recovery. So this is one exemplar profile of the movements made by one patient on the first day of therapy. And the heavy line is the real data, which we measured. And the little light lines are, we have an algorithm to fit submovements to that data. The submovements are support bound at log normal. I won't go into the details unless you ask me. But this is first therapy day. This is last therapy day. And you can see that while this movement is not perfect, it's not exactly the same as what you'd get from an unimpaired human subject, there's a clear improvement from here to here. And the improvement is characterized by these submovements. They make fewer of them. Each one of them is longer in duration, higher peak velocity, blended together better. And there's some indication that this is similar to the kinematic patterns that you see in the development of infant reaching, although that data is not quite as strong. So there's some evidence of these fragments or dynamic primitives in movements made by patients recovering. We also looked at unimpaired subjects, and we asked them to move slowly. And I don't know if you ever thought about it, but we tend to have a preferred cadence, not only to our walking, but to our moving. When I talk, I wave my hands around, but I don't wave them around like this. It's actually quite hard for us to move slow. If you don't believe me, take your arm from here, move it to here, but take 30 seconds doing it without stopping. Try it sometime. It's really hard. If you think that's easy, take your fingers from here to here, 30 seconds without stopping. You could actually see the little, you see the little hesitations? And it's not tremor. We are not very good at moving slowly. This is an experiment I did with Laura DiPietro and some other colleagues. We just had subjects sit in front of one of our planar robots that gives us a way to take the weight of the arm, provides us a simple way to record movement. Ask them to make, this is the dumbest, most boring experiment you've ever done. Move from this position to that position, stop. Move from this position to that position, stop. Keep doing that. Then do that at either your comfortable speed, or fast, meaning approximately twice that speed, or slow, meaning approximately half that speed. And this is what subjects did. First of all, subjects were able to obey the instructions. These are the actual speeds, mean plus or minus standard error for the comfortable, fast and slow. These are the paths they made, and as you should expect, there's some variability. Humans aren't perfect movement controllers, but they're basically roughly straight. What you then find, however, is that if you look at the speed profile along those paths, fast movements, you get a nice, smooth, single peak. Comfortable movements, there's some variation. Slow movement, a lot of variation. And notice that the vertical scale here is quite different. So as people go slower, fluctuations in their speed increase. Now, if you think about this from a point of view of mechanics, you can say, oh, well, you know, what's going on is you don't have a perfect internal model, so you haven't properly compensated for the dynamics or the muscle or whatever. But as I go slower, all of those factors decline at least as the square of the speed. So I might be able to account for deviations from ideal when I'm going fast, but when I'm going slow, all those factors go away. So what I'm seeing here is, strictly from biomechanics, these fluctuations should decrease with duration, but in fact they increase. And that, instead, rather than reflecting biomechanics, it reflects submovements. So we take the fast, comfortable, slow data, we fit the speed profiles to these support-bounded log-normal submovements, and with high statistical significance, you get more submovements as you go slower. And in fact, it turns out these are not simply a matter of making visual corrections because they're present whether or not you have visual feedback. Okay, so the story here is we seem to see evidence of dynamic primitives in motion control. And I would argue that what we saw in the stroke patients was pure serendipity. We were actually trying to work on helping them to recover. And we saw these, we didn't set out to look for these submovements, but you couldn't miss them. And they suggest the idea that maybe apparently continuous motions are actually chunked together as discrete commands. And then secondly, if you go look at our observations of poor control at slow speed, why should you be bad at moving slowly? Well, a high-speed performance limitation might be due to mechanics and muscle physiology. As I said, muscles are slow. But low speed, it can't be. That's got to be a software problem, not a hardware problem. Well, my favorite topic is physical interaction. And I've been saying this for a long time, but basically the key to controlling interaction is to managing this neuromuscular mechanical impedance. And if you're not familiar with it, think of it as like stiffness, only with dynamics. And if you want the math, it's not that hard. The only key requirement is that I have a dynamic operator that maps a motion into a force. And the only requirement is that the force and the motion have to be power duals. That is, force times F times dx has to be equal to change of work. With that gives you a very powerful way to think about physical interaction. And I want to make the case that I heard at least one person this morning talk about force control. And I believe in that. I think it's a great idea, particularly if you're trying to manage interaction. But remember, controlling force is not enough. You can't get there just with force control. So think of the fact that a very large number of tools look like a stick, right? A screwdriver is a stick with a fancy point. You know, there's the minus point and there's the plus point, right? Or you have a thing like a power drill. It's a stick with a motor and a fancy tip. Okay, well, if you imagine a stick pivoting about a contact point on a surface, I'm trying to drill a hole, I'm going to apply a compressive force to that to make sure that the drill or the screwdriver goes that way, not that way. If I just control that force without paying attention to motion, that system is now statically unstable because a small deviation of the stick from exactly lined up with the force generates a moment about that point, and the overturning moment grows with the size of the force. So that means that in order to keep this thing statically stable, never mind dynamically stable, I have to generate the equivalent of a translational stiffness in this direction. And not only that, but the minimum stiffness required for stability is proportional to the applied force and inversely proportional to the radius. So I can't push on stuff without also generating at least stiffness and in fact impedance. So in the minimum requirement, you got to do stiffness as well as force. Does that matter? This is by way of giving an example. This is actually some quite old work in which, with students, I worked on developing control for an arm amputation prosthesis. This is for a person who lost the arm above the elbow. We picked up electrical signals from the residual muscles in biceps and triceps and used those to control a prosthetic elbow. And the key thing that we did here was we used the difference of antagonist EMGs to set where the limb would be if there was no external force, and the sum of antagonist EMGs to set the effective mechanical impedance, in this case stiffness and damping, both of which increased with coactivation. We call this natural impedance control because it was our version of mimicking natural muscle behavior. And here's how we go. Can you bring the sound up, please? Not too
slow speed, second throw.
I should point out that this is actually a very difficult task because it requires accommodation of a constraint and coordination of a mechanical elbow with a natural shoulder.
I'm just thinking it's amazing.
This should fly. There we go.
Go as fast as you can.
Controller B, high speed. No friction, no weight.
Now, before I move on, notice that conventional motion control will not work well in this context because it requires too much information. The MPD would have to know the exact path of the crank and figure out what the exact motion of the elbow should be. What we do instead is say, look, the system gets out of the way, and it's not at zero stiffness, it's at a modest stiffness. It's at a stiffness that's modest enough to manage the stability of the combined natural mechanical limbs with the external constraint, and essentially gives us an easy way to get around multi-joint coordination. And now I'm going to ask for the sound to come back up again, if you could please. So this is a bimanual task, and it's not simply solving the linear complementarity problem. He's doing work. So he's not simply having zero force on the tangent, he's applying work to squish a piece of clay.
I'm amazed. I'm virtually simulating right now what my triceps would be doing if I had them attached to my elbow. I'm really, really amazed right now.
Controller B, trial 1.
So this is another bimanual task. I think you can see from the style of the socks that this is quite an old video, but one of the things I want you to notice as you watch is that he has no qualms about having this mechanical system interact physically with, say, his thigh. In fact, he takes advantage of that. And that's not trivial. That's part of one of the advantages that we get from this approach to control. The number of robots that are out there that you could do that with is quite small. So I think that's probably enough.
Yeah, 'cause, see, I can go like this.
So the point of that previous couple of videos was to show you that if you try to control impedance, it gives you at least one good way to manage physical interaction. But previously I showed you that there's evidence that humans are actually using motion primitives as well. And there's at least two kinds of motion primitives. There's these submovements, which are stereotype speed profiles, and there's rhythmic behavior, oscillations. So how do you combine these? Well, there's a tricky problem in here in that if you looked at these two different kinds of primitives, the motion primitives reflect motion planning, motor planning, and they actually live in the domain of information processing. But information processing is quite different from the physical world because it's only subject to constraints of causality and boundedness. There's no other constraints that I'm aware of, and if you know of them, please tell me. On the other hand, if I look at the primitives that dictate physically reactive behavior, they're in the domain of what I would call energy processing, and they're subject to numerous additional constraints like conservation energy and so forth, right? So these are different, these objects live in very different domains. So how can we combine them? Because clearly we need to, right? We do need to be able to not only just wave hands, but also do physically interactive tasks. So the approach that I've been exploring is to see if we can get away with repurposing the classical equivalent circuit. And if you have an electrical engineering background, I hope this is not new to you. If you don't, I'll see if I can explain. So equivalent circuits are an idea that goes way back, and once again we see Hermann von Helmholtz shows up. He was actually the earliest one to come up with what's in the US called the Thevenin equivalent circuit. There's actually 50 years between these two, but Thevenin's work was actually independent of Helmholtz's. There are two different kinds. The Thevenin circuit is the one which says I'm going to describe any linear circuit as a combination of two elements, an ideal voltage source and an ideal linear impedance connected in series, in fact. There's an alternative, which is the Norton. It's associated with Edward Norton in the US, although it's actually also associated with Hans Meyer in Germany. And interestingly, both of these guys published their work independently in really obscure journals in the same year and in the same month of the same year. So some of these ideas are sort of out there floating in the ether, and people pick them up. And of course, in this version of the circuit, it's a current source with a parallel effective impedance. And the notion of impedance is actually due to Oliver Heaviside. He's the guy that they named the Heaviside layer after. Very interesting character. Well, I won't go into that. But anyway, so the key idea of equivalent circuits is this is the history of their development, and they give you two big benefits. One is they give you a spectacular simplification. So you can take a circuit of arbitrary complexity, and if it's linear, I can come up with a functionally equivalent form that has two components, and that's it. Not only that, but both of those components are experimentally identifiable from measurements made at the outside. I think that's important if I'm trying to understand human behavior, because I can't open the hood. I can't get inside the box, at least not easily. I really would like to be able to do things based on external measurements. The reason I'm interested in this is because if you think of it, for linear systems, equivalent circuits serve as interface elements. The source elements describe the forward path dynamics from a desired voltage to an actual voltage that shows up at the interface. And that's independent of any interactive behavior. And on the other hand, the equivalent resistance describes interactive dynamics independent of the forward path dynamics. So what I want to do is see, can I get away with repurposing the idea of an equivalent circuit into something that will work for nonlinear systems and will allow me to describe both informational dynamics and physical dynamics. And here's the basic idea in block diagram form. The idea is that I have some motion command that's specified. It'll be composed, say, of oscillations, submovements. It's got some dynamics that leads to a trajectory which I'm calling the zero force trajectory. That is where the system would be if there were no external forces. And of course, it's a fiction because there are external forces. But then deviation of the actual motion from this zero force trajectory it's the input to this operator that generates forces as its output. And so the idea here is that in the information domain, I've got the equivalent source. It's composed of motion primitives. The equivalent resistance is in the energy domain, and it describes interactive dynamics. So the idea here is this is kind of sort of a neoclassical approach. I'm going to take the classical equivalent circuit, extend it to nonlinear dynamics, and see if it can describe this information-energy interface. Well, a question that should come up is, are there any constraints on this model? Well, one of the key properties of physical systems are their invariances, and I think it's fair to say that all of physics is the study of things that don't depend upon the coordinate frame. Would you agree, Daniel? Daniel says yes. So, I mean, this is most famously in Noether's theorem, and Noether's theorem is, if you look at Hamiltonian mechanics, then you can associate invariances. Say time shift invariance gives you conservation of energy. Rotational invariance gives you conservation of momentum, and on and on and on and on. So invariances are really critical. Okay, I'm thinking about interactive behavior of a human or a robot. And one of the things I'd like to have is translation invariance. That is, if I translate the reference frame, the interactive behavior shouldn't change. And you can either think of that in terms of an externally imposed reference frame, or you can think of it from the point of view of the robot. I'd like to have the robot be able to do something over here and do something over here and not have the location in the workspace matter too much. Now that might be challenging. For example, if I stay with fixed space robots, then at some point I fail to have this translation invariance, because at some point the robot can only have a limited reach. But I'm not stuck with fixed space robots. I could also work with mobile robots. And with a mobile robot, I could walk around to the place where I'd like to get the right behavior. So I think translation invariance is a reasonable thing to require. It's a subtlety because it's very tempting to think about force control And one of the ways to think about that in the context of this notion of a nonlinear equivalent circuit is to say, what I'm going to do is I'm going to specify a nominal force as a function of time, and I'm going to include this interactive dynamics as an impedance that modifies that force. And if you don't understand what I mean by this, think of it as actual force is nominal force minus the stiffness times the displacement. It's kind of like a generalized spring, right? And so this is a perfectly reasonable thing to do. One of the things, however, that concerns me is if I now take the coordinates and I translate them. So I define a new coordinate frame, which is x prime is the old coordinate frame plus some constant, and I plug that in here. Well, I can substitute easily enough, but now what I find is that this term that used to be the force source, it now depends upon where the reference frame is. That is, it depends upon C, and it depends upon the effective stiffness. So I don't have a translation invariant representation. I've got one that at least one of the elements, this force source, changes with the location of the origin of the coordinate frame, and not only that, it depends upon the effective stiffness. In contrast, if I go look at, instead I go look at nominal motion control. So even when I want to control force, I'm going to specify a nominal motion. My interactive dynamics are then going to generate force as a function of deviation from that motion. And if this is not clear, think about it like a spring. So here's force is spring constant times displacement, which is displacement from this nominal motion. Now I translate the coordinates. I do the same thing now, and I translate the coordinates for the actual position and for this zero force position. That leaves the delta stays the same, so I wind up with a translation invariant representation. So what we have here is, if I ask for invariance under translation, then what I get is that my nonlinear equivalent circuit, my nonlinear equivalent network, provides a sort of a canonical model that'll cover both mechanical, energetic, and informational domain. But surprisingly, it requires that I specify motion, not force, as the nominal behavior. So that's by way of, it's probably a nuance. And this is I think this is a good way to represent interaction, but maybe it's not that big a deal, but we'll see. So I then go about the question of how do you choose impedance? And one of the ways to do it is to say, look, I'm going to assume that I have a good learning engine, and I'm going to make the assumption that my learning engine is loosely analogous to optimization. And I'm not going to get into the details of the algorithms, partly because I don't know them, and there are people in the room who are much more expert on that than I am. But the one thing that's probably an obvious observation, but I think it's worth stating anyway, is that if I want you to learn impedance, then you have to include both force and motion at the interface point in the penalty function. And at the interface point is important. That is, it has to be force and motion at the same point. Once you do that, basically an impedance falls out of the optimization. And to show you that, I'm going to do a really, really toy example. I mean, this is about as dumb as I can get away with, mostly because I can't handle the hard examples. So this is a bit of a busy slide, but let me walk through it. Imagine I have imagine my manipulator consists of a mass, a spring, a damped spring, something that can move the end of that spring. So I can move the mass of the manipulator by pulling on that spring. Then I have it interact with another object which has mass. So here's my object model has a mass, m sub 0, subject to some perturbations. I put them in there so that my optimization problem is well posed. I'm going to take their magnitude of the Gaussian noise to 0 in the limit. I compute the interface force as the mass m0 times the acceleration, and I have now this is the mass of the manipulator, this is the mass of the object, this is the total mass. Here are my dynamic equations. They're fairly straightforward. It's simple second order system. I develop a cost function that includes a quadratic penalty on force scaled by a force tolerance, and a quadratic penalty on displacement displaced by a displacement tolerance. And because I stick in stochastic noise, I have to take the expectation of that. And now what I want to do is select the parameters, both the stiffness and the damping, to minimize this cost function, that is the expected value of that. It turns out that because this is a dumb, simple enough example, you can actually solve this in closed form. Of course, you're not going to get it in general. But what you wind up with is two things. One is, as you might expect, the optimal damping combines with the optimal stiffness and the total mass to give you a damping ratio of 0.707. That's sort of standard linear quadratic optimal result. But you also get a number for the optimal stiffness. And of course, in some senses, it's sort of obvious in that the optimal stiffness is determined by the ratio of the tolerable force and the tolerable displacement. Seems easy enough. But it's multiplied by this ratio of the total mass to the object mass. So I bring this up only to make the point that, well, 2 points really. One is include force and displacement in the cost function and you'll get an impedance out. And secondly, some of the results are a little bit counterintuitive. And that leads me to the following. I didn't go through the details, but there's a minimal impedance required for stability. The optimal impedance depends upon force tolerance, but it's also weighted by the ratio of total mass to object mass. And that implies that if you have a manipulator with an apparent mass that's large, then that means that your optimal stiffness is actually bigger. And most present-day robots vastly outweigh the objects that they manipulate. So that says that most present-day robots should be very stiff and highly damped, and in fact they are. So even though you think that you should have compliant behavior to avoid damage to the object, in fact, this is going to tell you that large apparent mass will require greater optimal stiffness. By way of an aside, let me just briefly mention, we've been playing with the Baxter robot from Rethink to get it to do contact tasks. And by the way, I completely agree with, was it Emma who said that we should work with cheap robots? So this is not quite as cheap as, this is about $20,000 robot. But it's really nice to work with because you don't kind of worry too much about breaking it. And the company that makes it is just across the river anyway, so we can probably get it fixed. But we asked it to do simple tasks. It's a dual-armed robot, and we have it doing an interaction task here, and this is sanding a surface to show that we can actually use Baxter to do real work. But the key thing is that the apparent mass matters. And let me show you. We've done some identification experiments to measure the effective apparent mass of different parts of the Baxter robot. What you're seeing here is the fit of our model down here to experimental data, and it's pretty good. But the thing to notice is that if we just took the data from the Rethink website and computed the link inertias, we would be off by about we would have forgotten the reflected motion, the reflected motor inertia. It's about 2.6 times the link inertia. And in fact, if you compute the effective hand inertia, this is just I'm looking at, imagine you're looking down at a plane and I'm computing the effective inertia towards the shoulder and laterally. This is for a human by comparison. This is for Baxter if I forgot about the fact that I have real inertia in the motors, and this is Baxter with the actual inertia, and that's something like almost over a factor of 2 greater than what we would get otherwise. So apparent mass matters, and you have to pay attention to it. But that was somewhat of a digression. So bottom line here is optimizing impedance is if I include interface force and motion at the same point, then I'll get an impedance as an output, and that's easy enough to formulate. Unfortunately, if I allow the problem to have variable impedance, which is what I want, then that turns out my optimization problem into a non-convex optimization problem. And this seems to be fundamental. I can give you the arguments for that if you want. And non-convex, as people in the room know better than I do, means very hard. So I don't know how to solve that, but apparently there's some recent work that's been done. There's some old work by Tamar Flash, but some more recent work by Jonas Buckley and a group in Singapore. So it may be tractable, but I don't know enough about it to give you a clear statement about that. So getting back, I should probably try to wrap up now, is I think that dynamic primitives are one of the tricks that the biological system uses to get around its own hardware limitations. The dynamic primitives include motion primitives like submovements and oscillations, but also you need something to manage interaction, and I think mechanical impedance is such a thing. You can combine those by using this nonlinear equivalent networks. And remember that if you want to have these invariances, the output of the forward path dynamics, the bit that's in the information domain, should be motion, not force. And you can characterize the learning of the of the impedance as an optimization problem. Now, it may be a hard one, but at least you can formulate it. But the question that I have, and it's really a question I'm going to leave open, maybe Daniel can help me answer it, is does this representation, this combination of dynamic primitives, imply some sort of a geometry? So we know the geometry isn't Riemannian, at least for haptic behavior. So what kind of geometry do I get? I don't know the answer, but maybe some of you people can give me some ideas. So with that, let me stop and thank you for your attention.
Before listening the answer by Daniel, and there may be some question perhaps in the audience. Yes, David.
So I have a question related to what you say when you move slower, you cannot explain why you see the velocity profile you see because of the mechanical system. So in my experience with robots, moving slow is really hard because of friction effects. Could have been something similar with the human? It's a very naive question, but it's just like to know why this cannot be a mechanical property.
Okay, so the reason that I don't think you can account for that phenomenon in biology is because biological joints have spectacularly low friction. If you go look at the effective coefficient of friction of the hip joint, it's essentially zero. It's a fluid film between two quasi-elastic surfaces, and it's being measured essentially at zero effective friction. It's possible that there are some hysteretic nonlinearities in the muscle that might account for this, but what we see in these experiments is that in fact the subjects the muscles are they're active at a fairly high level, even though that requires simultaneous activation of opposing muscles. So surprisingly, as you go slower, you need less torque. So you should see reciprocal activation only. In fact, you see elevated co-activation.
So the impedance is changing when you go slower?
Yes, even though this is for a non-contact task. You can even ask subjects to do this in the air, that is, move from here to here, only go real slow, and you'll still see the same thing. So it doesn't look, I don't know of any mechanical or biomechanical phenomenon that can account for this.
A computer is not a brain, a robot is not a human, so the hardware is different, so maybe it doesn't require software to control it, it might be different. But let me be more precise. I'm still wondering, do we really need to control impedance in a precise way? I mean, it is obvious that we need some form of impedance for control, make a very strong point there. But do we really need to control like this specific value for impedance, or is it just have some other combination of motion and force?
Okay, so I think the quick answer to your question is I don't know, but let me give you a longer answer. I think that there are requirements that are placed on impedance. So this morning I asked Emma about passivity. So if you take a robot that's got force control, that is, you have a force sensor at the endpoint of the robot, and you try to close a feedback loop and control that force, then you're very likely to run into to either of two problems, one called contact instability and the other called coupled instability. Contact instability is where the robot is fine until it touches down, and then when it touches down it starts to bounce. And what's happening is that you've actually inadvertently set up the controller so that it dumps energy into the interface. One solution to that is to ensure dynamic passivity. You make the robot look like it behaves like some collection of springs and masses and dampers. To ensure passivity in the presence of feedback is not trivial, because any delay in a feedback loop violates passivity at some frequency. So I think there is a requirement for some precision in impedance, but I don't know what it is. But again, my honest answer is I don't know.
I have a question about the haptic representation. You said that the circle, the subjective circle turned to an ellipse. Does the ellipse shape depends on if it's located in the frontal plane or in the sagittal plane, or in particular place in the space?
Spectacularly good question. That was great. I wish I had time to go into this at length. It turns out that you can think of it in terms so the answer is yes, it depends. And you can think of it as, it's probably just as well to think of it as, which rectangle looks like a square. And as I go further towards the limits of reach, the rectangle gets real skinny. In about this position, it's about that shape. And if you extrapolate, we've done measurements in 3 different locations. If you extrapolate, the square would look square about over your shoulder. It also it varies with location, but it seems to vary. The distortion seems to go along polar coordinates.
And do you think there is a relationship with the metric that is used for the exteroceptive representation of space?
Well, yes and no, but my sense is there isn't a metric. I don't know how I come up with a metric that won't allow me to coordinate angle and length. I mean, somebody who's a geometrician, tell me about that. Now, there's clearly I have some sense of length, and it may be distorted, but I have a sense of length. It's just I don't think I can describe that as a standard Riemannian metric. In other experiments we've done, again, I could talk about this for a couple of hours, we asked subjects to just draw circles with eyes closed. So close your eyes, draw a circle, and tell me when you've drawn a good one. Then we take 5 cycles around that, fit that to an ellipse, and we find that ellipse based on blind circle drawing matches the ellipse based on length perception, but doesn't match the ellipse based on angle perception. We had another experiment in which we asked subjects to judge direction. That is, present them with a series of virtual slots. Feel along that slot. Tell me when it's straight ahead or straight sideways. And you give them a whole range of them. Again, from that you can get a metric, and that metric turns out to be, it's statistically weaker, but it's consistent with the angle perception metric. So it looks like, at least in the context of this kind of experiment, your angle judgment or your direction is consistent with angle, but not consistent with length, but length is consistent with motion. So the impression I have is that the brain has developed modules that are good at certain pieces, like reaching to a point, but it hasn't fully integrated them into a consistent geometry, which is what we assume when we write down classical mechanics.
Okay, thank you very much. I have several exciting several questions that is exciting to me. And the first one that I want to ask 2, but first one is about where are the dynamic primitives located?
That's a hard question, and
because you said that the dynamic primitives compensate the long time delay, communication delay.
Yes.
To me, it looks like somewhere in the body or spine, but the neural recovery example, I think the patient is recovering in the brain.
Okay, so let me.
Am I missing something?
No, you're quite correct. But so let me. So the first question, where are they? Again, I have to tell you, I don't know for sure. However, my best guess is that they're actually implemented in the spinal cord, probably midbrain and lower, but at least down there. Now, you're quite correct. Stroke patients, most of the stroke patients that we see, they have either basal ganglia or cortical lesions from basal ganglia on up. What's going on is that their ability to evoke these submovements has been impaired by the injury. But then as they recover, they get better at evoking them and stringing them together. So I think that they are implemented low down in the brain. I think midbrain, possibly spinal cord. But I'm hand waving, as you can see.
Yes, well. So maybe you use a different word, but to me, you explained that impedance is the internal model of the human to interact with the external environment at the interface. That's
okay.
The question is why? Why do we have that internal model?
So I think, in the first place, I think there are two things that are important. One is that the physical impedance matters whether you like it or not, or whether the brain pays any attention to it. No, so the physical interactive behavior, I think, it's there and it's important. My speculation is that the brain actually has some representation of that. So you do have, what form it takes, I don't know. For example, it just could be a general pattern of global co-activation of opposing muscles. But I think that is part of what's represented, pre-computed before you launch a movement. So when you go to make a movement, my favorite example is, imagine that you're in a strange hotel in a city in France where you can't speak the language and it's dark. And I need to go to the bathroom, but I got to turn on the light switch. Well, I don't go to the wall doing that, right? Because if I walk at a finite velocity towards the wall and I hit with the tips of my fingers, it's going to hurt. So I know how to make things kind of soft and floppy, and so I'll do something like this. And I think, and I'm speculating, I think that the brain at least knows that much. And that's in the internal model. But then you also have to be able to implement that. And that's, I think, the implementation of that impedance is out in the periphery. Don't know if I...
Deform the ellipse for haptic geometry. You know this experiment of Condering, about the fact that we make a very false judgment of alignment, false judgment, also false judgment of the middle of a segment, but we still correct to have right inference from geometrical theorem. So in some sense, perhaps in your case, you could have very bad figures, but also compose them as if the plan is really Euclidean. Do you look at this kind of secondary effect? The fact that it could be just a deformed representation of a correct Euclidean geometry.
So as I said, I mean, I probably didn't present enough of this, but if you look at the metric that we get from their angle perception, it's completely inconsistent with how they actually generate movement. So when we ask subjects to generate a circle, they don't generate a circle, they make a wiggly ellipsoid, basically. And that ellipse does not match with the ellipse that you would get based on their angle judgment. So they're not consistent. So basically the angle and the length are not consistent. Direction and... Okay. Well, curvature can give me a distorted. I mean, I can imagine a geometry that's a distorted geometry. Like I looked at Euclidean through a lens that twisted it without tearing it, but I'd still get a locally Riemannian metric, right? But in that case, shouldn't angle be consistent with length? Okay, so piece. I mean, I agree, but I don't know that there's any evidence that the distortion is as non-smooth as to make this not local. I mean, I agree we haven't gone down to tiny because we haven't been able to do that. But how in order to have this not be a good representation of a local metric, you're going to have a very rapid change of the you're going to have to distort the Euclidean quite rapidly with space. We're looking at something that's about that size, right? So, okay, that's not local, but it's pretty small. Small compared to my workspace. Okay. But you're quite right. We haven't done the teeny tiny experiment.
Okay, then I propose that to stop here and thank the speaker again.